Okay, in this video we're going to look at a man who is 1/4 of the way up a ladder that is resting against a smooth, frictionless wall. And so the force acting here is just going to be the normal force, perpendicular to the wall. Okay, so the wall you would imagine being like this. Normal force is always perpendicular to the surface. The friction is not existent for that, but there is friction down here. It's going to be parallel to the surface, and that is static friction. We also have a normal force from the floor, which we can put in, and I think this looks like about halfway. And this is where the weight of the ladder gets shown, and then 1/4 of the way would be here, and this is where the weight of the man can get shown. So it's 10 meters from top to bottom. Okay, so that's 10 meters. We know it's 5 meters to there, and then getting a little bit tricky to show this, but 2.5 meters from there to there. All right, let's see, are there any forces we missed? We've got the man pushing down, we've got the weight of the ladder itself, and we have the normal force from the wall. Now we do need to differentiate those, so that's normal force wall, and this is normal force floor. And then we've got the friction from the ground. All right, so we're supposed to find this force here, and this one, and this one. Okay, so we were given the mass of the ladder and the mass of the man, so we can easily find those weights, and then we need to find everything else. So we have 3 unknowns, so we know right away we're going to have 3 equations. We're going to say up is the positive y direction, to the right is the positive x direction, and counterclockwise is my positive direction for torque. So we can sum forces in the x direction. Everything's equilibrium. So we know that the acceleration is going to be 0 in all of these. So we don't know either of those. So we can't solve that equation. We just know that each of those is equal to each other. And we can sum forces in the y direction. And so that gives us F in floor. Oh, sorry, I was supposed to put equals MAY here. So F in floor minus, let's see, we have 20 kilograms times 9.8 meters per second squared. That's for the ladder. Minus 80 kilograms times 9.8 meters per second squared equals 0. So this is the normal force from the floor, and that is going to be equal to 980 newtons. So that's one of our unknowns. So we've used our summation of forces in the x and y direction, and at this point we're going to need to sum the torques relative to some axis of rotation. Now the things that are unknown at this point, we now know this one, so we've got the frictional force here and the wall force. So those are the 2 unknowns. So we could just make this our axis of rotation right here, and then we can sum the torque. Let's see. And when you sum the torque, it's equal to I alpha, that's moment of inertia, times angular acceleration. This is a equilibrium problem, so the angular acceleration is 0. And so now we need to go ahead and sum the torque. So the friction is not going to create any torque. The normal force from the floor is not going to create any torque. But the weight of the man, which is 80 kilograms times 9.8 meters per second squared. That's his weight. and then he is 2.5 meters away. And then we need to be careful here. We need to take a look at what the angle is between R and the force. So let's go ahead and draw that in. Let's change colors here. And so we'll draw in our R vector, which goes right here. So that's our R vector. That's 2.5 meters. But we need to know this angle right in here. We were told that the ladder makes an angle of 60 degrees with the ground. So this angle here is 60 degrees. And if we look at this triangle that I can trace out right here, that's a 90-degree angle. So that means this is a 30-degree angle. So we're going to say that's times sine of 30 degrees plus the weight of the ladder, so that's 20 kilograms, times 9.8 meters per second squared times 5 meters, also times the sine of 30 degrees. And I'm running out of room here, so I'm going to go into a second line. So both of these weights are going to cause a clockwise rotation, which is a positive torque. The normal force from the wall, though, is pushing to rotate it around clockwise, so that's going to be negative. So we say minus the normal force from the wall, that's our one unknown in the equation, times 10 meters. And then we need to figure out the angle in this case. So if we continue this R all the way up to there, now we need to figure out the angle here, or we could extend the normal force of the wall. We could write it here instead and figure out this angle. And so in that case, we could say this is horizontal, and the ladder, if we look at this horizontal line down here, representing the floor, and this horizontal line up here, it's just a horizontal line, then we could say this 60-degree angle and this angle right here are opposite interior angles, and so that makes a 60-degree angle. Or we could draw a vertical line down here and say that's a 90-degree angle, this is 60, and so this angle right here is 30, and so that means this part right here has to be 60. So there's various ways to do that. That comes out to be a 60-degree angle, and so then that's equal to 0. And now we have quite a bit of, we need to do the calculations, type a bunch of stuff into our calculator. I'm going to leave that as an exercise for you to do, but ultimately the normal force of the wall comes out to be 169.7 newtons. We could round that to 170. And we see up here that the frictional force is equal to the normal force of the wall, so that's also equal to the frictional force of the floor, and that makes perfect sense because there's only two horizontal forces, and so they have to be equal to each other.